I'm going to talk about Coulomb's law and fields. I would recommend you watch my introductory video on charge and electric forces first. All right? So you may know that if you have two charged objects, if the net charge on each is of the same type, the electric force will be repulsive. If the net charge on each is of different types, the electric force will be attractive. Now, what about the magnitude of the electric forces? All right, how many newtons are those electric forces? So that's what Coulomb's law helps us with. Give me a minute to make a picture, and then I will elaborate and continue. All right, so my picture denotes two charged objects separated by a distance d. The charge on the left object is q sub 1. The charge on the right object is q sub 2. Traditionally, the variable q is used to denote some amount of charge, so I'll continue that tradition. All right, so each charged object will experience the following force. K times Q1 times Q2 divided by d squared. All right, where K is equal to 9 billion Newton meters squared per Coulomb squared. This is the Coulomb's law formula for electric force. This will allow you to calculate the magnitude or the strength of electric forces. Okay? Now, notice that structurally it's very similar to the formula for the force of gravity. For the force of gravity with respect to two objects separated by a distance d, okay, with two masses, we multiply the masses together, we divide by d squared, and we multiply by a constant. Okay, here we are doing something similar. We still divide by d squared. Instead of multiplying masses, we multiply charge, and we still have a constant in front. For gravity, the constant was that, remember the capital G, the gravitational constant? Here, it's K, which is referred to as the electric force constant. Now, I'm going to do some examples using Coulomb's law, but let me make a comment about the sign of the answer. If you think about it for a moment, you'll notice that if you have similar types of charge, if you have the same type of charge, that the product Q1 times Q2 will be positive. And if you have different types of charge, the product Q1 times Q2 will be negative. So you might think that it's a good idea to treat positive answers as repulsive forces and negative answers as attractive forces. I would not suggest that you do that. I would suggest you take the absolute value of what you get from Coulomb's law. Okay, the calculation. Take the absolute value. Use that to calculate the magnitude of electric forces. Okay, and find the direction of electric forces in a separate step. Okay, by stepping back and asking yourself, okay, in this situation with this pair of charges, what direction would the electric force be for this object? Okay, don't use Coulomb's law for directions. Only use it for magnitudes. All right, with that caveat, let's do some examples. Suppose that we had two charged objects separated by 6 meters. Let's say one of the charged objects had a net charge of plus 2 coulombs, and the other charged object had a charge of minus 3 coulombs. So what would be the magnitude of the electric force that each charged object would experience? Okay, so we can use Coulomb's law. K times Q1 times Q2 divided by d squared. So that will give 9 billion times 2 times 3. Now remember that I'm not concerning myself with the sign of the answer. So I'm going to ignore the negative sign on the second charge amount. Divided by 6 squared. Okay, and you can put that into your calculator, or you can just kind of play with it. Let's see, 2 times 3, that cancels one of the 6's downstairs. So then you have a 9 over 6. 9 over 6 is 3 over 2, 1.5. So the answer is 1.5 times 10 to the 9 newtons. Now, this is what I was suggesting. So now you sit back and you calmly do this second step. So you look at, okay, what do we have here? We have two objects. The charges are of different types, so therefore the electric forces are attractive. Okay? Now I'd like you to try an example. Here's an interesting one. So suppose that I had two electrons that were 1 meter apart. I want you to find the ratio of the magnitudes of the electric force and the gravitational force. Okay, the ratio of the magnitudes of the electric force and the gravitational force. Let me remind you, if you don't know, that the charge of an electron is negative 1.6 times 10 to the minus 19 coulombs. You can also Google or do an internet search for that. And the mass of the electron, you can also do an internet search for that, but I'll tell you, that is 9.1 times 10 to the minus 31 kilograms. And then you will need the gravitational constant. I'll go ahead and give that to you as well. 6.67 times 10 to the minus 11 Newton meter squareds per kilogram squared. All right, so pause the video and try to find that ratio now. All right, so I'll go ahead and do it as well. So the magnitude of the electric force will be K times Q electron squared, all over 1 squared. The magnitude of the gravitational force will be G times the mass of an electron squared divided by 1 squared. So I can ignore the 1 squareds, and I have K times Q electron squared divided by G times the mass of an electron squared. and that gives 9 times 10 to the 9 times 1.6 times 10 to the minus 19 squared, all over 6.67 times 10 to the minus 11 times 9.1 times 10 to the minus 31 squared. So go ahead and plug that into your calculator if you like, if you haven't done a similar calculation already, and you will see that you will get the following answer. 4 times 10 to the 42. Now, let's get a sense of how big of a number that is. So 10 to the 6 is a million, 10 to the 9 is a billion, 10 to the 12 is a trillion. So we have 4 million trillion here. All right, let me say that again. 4 million trillion. That is, that number corresponds to how much bigger the electric force is with respect to two electrons. Okay, you might have heard that almost all of chemistry is based on the electric force. Okay, that is the reason that reactions happen, that all that wonderful chemistry happens. All right. Yes, it's true that atoms and molecules and electrons and protons, that there's gravitational forces involved, but compared to the electric force, it's negligible. It's irrelevant. Okay. The electric force by far dominates what's going on. All right, now I'm going to show you an example of a slightly more complicated situation. Suppose we had the following picture. So give me a minute to draw it. Okay, so I have 3 charged objects lying on a line. Objects A, B, and C. Object A has a net charge of plus 4 coulombs, and it's 5 meters away from object B. Object B has a net charge of minus 6 coulombs, and it's 5 meters away from object C. Object C has a net charge of plus 10 coulombs. Now, how would we calculate the total force on object A? Okay, so object A, here's how you can reason it out. Object A is experiencing an electric force from object B, but it's also experiencing an electric force from object C. What we need to do is find the electric force vector for each of those pairs, A and B, and then A and C, and then we do a vector sum to find the total force. All right? So let's first find the magnitude of the electric force with respect to objects A and B. So I'll denote that by F sub AB, and that's equal to K times Q sub A times Q sub B divided by the distance between A and B. I'll denote that by D sub AB squared. Now, I'm interested in the magnitude, so I'm going to put absolute value bars around the product of the charges. Okay? And so there is one of the charges, or excuse me, one of the forces. All right, and then we also have FAC, right? This is the electric force with respect to objects A and C, and that would equal, the magnitude will equal K times the absolute value of QA, QC divided by D, we'll call it D sub AC squared, the distance between objects A and C. Okay, now we step back and we deal with directions. So objects, the force with respect to objects A and B would be attractive. The force with respect to objects A and C is going to be repulsive. All right, so the two contributions are in opposite directions. So we have to find the difference in the magnitudes. All right, why don't we subtract F sub AC from F sub AB? So FAB minus FAC. Now, F sub AB is to the right, so if the answer is positive, we know that the total force is to the right. If the answer is negative, we know that the total force is to the left. All right, so let's go ahead and work that out. So 9 F sub AB, 9 billion times 4 times 6. Remember, I'm ignoring minus signs. Divided by 5 squared minus 9 times 10 to the 9 times 4 times 10 divided by, and now the distance between A and C is 10 meters, isn't it? So 10 squared. All right, let's see what we can do with that. So, you know what? Let me factor out the 9 times 10 to the 9 first. 9 times 10 to the 9, and the first fraction had a 4 times 6 divided by 5 squared. That's 24 over 25, right? The second fraction had a 4 times 10 divided by 100 squared. That's 40 divided by 100. Okay, and let's see, 40 divided by 100 is 10 divided by 25. Common denominator, we like that. So that gives 9 times 10 to the 9 times 14 divided by 25. All right, so that is positive, so we know that the total forces are going to be to the right. So that gives 5 times 10 to the 9 newtons to the right. All right. Now, I would like you to do a similar problem. Give me a minute to make another picture. Okay, once again, I have three objects lying on a line. The objects are denoted by the letters A, B, and C. The net charge of object A is minus 6 coulombs. The distance between objects A and B is 4 meters. The net charge on object B is plus 3 coulombs. The distance between objects B and C is 3 meters. The net charge of object C is minus 4 coulombs. Okay, now here is the challenge. I would like you to do the following. Find the magnitude and direction of the total force on object B. Okay, so pause the video and try to do that now, please, if you like. Okay, so I'll go ahead and work it out as well. So first I'm going to find the magnitude of the force with respect to objects A and B. Then I'm going to find the magnitude of the force with respect to objects B and C. And then after I find those magnitudes, then in a second step, I'll determine if I have to add or subtract them based on the directions of the forces. All right, so with respect to B and A, we have K times Q sub B times Q sub A all over the D sub BA. Okay, where D sub BA denotes the distance between objects B and A. And then Q sub A is the charge on object A, Q sub B is the charge on object B, and then in a minute I'm going to write Q sub C, which is the charge on object C. Alright, so BC, F sub BC, we have K times Q sub B, Q sub C, all over D sub BC, where D sub BC denotes the distance between objects B and C, and I don't care about signs, so I'm going to put absolute value bars. All right, so let's see. So the electric force with respect to objects A and B is attractive. The electric force with respect to objects B and C is attractive. However, this is important. Even though we have two attractive forces, notice that they're each pulling B, object B, in different directions. Okay? So this goes to the point I was making before about not relying on Coulomb's law to give you the direction of forces. Yes, here we have two attractive forces, but that tells you nothing about the direction of each of the forces. Okay? Think about that. So we've got two forces in opposite directions, so I'm going to subtract the magnitudes. And let's see, F sub BC is to the right, so why don't I put that one first in my difference? F sub BC minus F sub BA. And one reason to do it in that order is that if I get a positive answer, that will mean that the total force is to the right. And if I get a negative answer, it'll mean that the total force or net force is to the left. All right, so let's go ahead and do it. So BC first. 9 billion times, let's see, 3 times 4, remember ignoring signs, divided by 3 squared, minus 9 billion times 3 times 6, again ignoring the sign of the charge for object A, and then we'll divide by 4 squared. Okay, and let me factor out the 9 billion again. Again, I mean like I did on the last problem. So let's see, we have 12 over 9 minus 18 over 16. All right. So you can hopefully see that that will give a positive answer, so the net force will be to the right, and you can punch that into your calculator and get 1.9 times 10 to the 9 newtons. And as I said, it's to the right. 1.9 times 10 to the 9 newtons to the right. Okay, now I would like to switch gears and talk about fields. Okay, here's a puzzle for you. Imagine you have two charged objects separated by some amount of distance in a vacuum. Okay? We know that those two charged objects will experience electric forces, right? Let me ask you a simple question. How is each object able to reach across empty space and exert an electric force on the other object? If we observed very closely the space between the objects, we wouldn't be able to detect anything reaching out between the objects, right? So how does that happen? This was a mystery that puzzled people for a long time. Today, we understand that what happens is the following. Charge creates surrounding fields. All right, what does that mean? So, whenever you have charge, in some strange way, it modifies the surrounding space. Let me give you an analogy. Think about opening a perfume bottle. Doesn't the scent eventually permeate through the whole room? So in a sense, the perfume has modified every point in the room, every point in the space. Okay? Think about if you drop some red food coloring in a swimming pool and come back a long time later. The red food coloring will eventually diffuse through all the water, and if you put enough, it'll be probably some shade of pink, all right? But eventually, doesn't all of the particles of the food coloring diffuse and contaminate every point in the water? Okay, so let those be your images to think about what charge does to the surrounding space. Somehow it modifies the space, it contaminates the space, if you want to use that word, and how much it affects each space is given by field values. Okay, and so to answer the question of how another object can feel an electric force, what it's doing is it's being affected by the field. Okay? Now, again, there's a lot more I could say about this topic. People have advanced the topic for years. Let me just mention that there are two types of fields people work with regards to charges. We've got the electric field from charge, and we also have something related called the electric potential field. All right. If you're curious, masses have gravitational fields. Okay? So they, in a sense, affect, modify, contaminate, whatever you want to call it, the surrounding space as well. Okay?